How's it going, Doc Dean?
Mr. Dr. Charles Dean in the flesh. How's life going?
Just trying to survive. I'm sure you guys know how it is.
Well, you know, the state's gonna open back up soon.
Yeah, that's what they say.
I'm nervous.
Yeah, I don't know about all that.
Why are you nervous for, Poppy Watto?
I'm dead. LOL. But I don't know, because like, come on, what was the whole purpose of shutting down school for 2.5, 3 weeks just for us to be back out in the malls and on the beaches? Like, that's irrelevant.
That's what the news says.
That's what I'm saying. So if that's the case, we should have stayed in school.
Well, like, we should stay in school though. We should be infected by now.
I don't know. Well, I mean, I feel like the people who got infected at school only got infected because they went home and went out. You see what I mean?
Exactly.
I don't know.
But all it takes is one person to come back to the school infected, and then
everybody, right?
Everybody else.
But listen, I'm gonna tell this right now. I'm not gonna let no virus try to infect me to it, because I always try to find my way to survive.
Right.
And that's real talk, for real. you laugh, Paul. I'm dead serious right now. Dead serious right now, man. It is what it is.
So let's see. All right, let's let everybody get in, get settled. We will get running here in a second. All right. So, yeah, so I'm not sure exactly what was going on previously. It's like the meeting's supposed to have a waiting room so that you guys can, join a couple minutes early if you'd like, but it won't mess up the timer. But then the meeting was getting started with the when you all started to join, so the waiting room wasn't working, so I don't know. But I think we are all set now. Okay. So we have been talking about light, reflection, and refraction. So real quick, what is the law for reflection? What's the law of the relationship, the equation that governs that?
Is the law of reflection is theta I equals theta R?
Yeah. So I'm just going to call them 0 and 1. So the initial angle of the
Mhm.
incoming ray, the incident ray, is equal to the angle of the outgoing ray. What
Right.
about for
Refraction. Is it N1 sine theta 1 equals N2 sine theta 2?
it is exactly that. So for refraction, we look at the indices of refraction, and they weight this equation accordingly. So the index on material 1, so wherever the ray starts, and multiplied by the sine of the incoming angle equals the index of the second medium times the sine of the outgoing angle. And these two little facts govern all of reflection and refraction. So when you have a incoming light ray, this is how this determines whether or not partially it determines whether or not it will reflect or refract, or how much of it will, and mainly it determines the angles of refraction, ingoing and outgoing. Okay. So one of the things that this kind of comes out of this is, so we had the index of refraction being a simple number is kind of an oversimplified aspect. We just say that the index of refraction for a certain material is this. Like for diamond, it was like 2.5-ish. But in reality, it's not exactly like that. In reality, the index of refraction depends on the wavelength of the light that's coming in. Remember, we said that this whole idea of refraction is based on the velocity of a wave equals frequency times lambda. And what causes refraction, what causes the light to turn, is that the velocity is different inside a different medium. So since the frequency has to stay the same, if you make the velocity smaller, you're going to make the wavelength smaller. And this is what causes refraction. But it's not actually just that simple. The index of refraction in also depends on the wavelength. So where in we said was the speed of light in a vacuum divided by the velocity in that material. This actually is dependent on the wavelength. So just a second. So certain wavelengths have a higher refraction and some have a lower. So let's think about what this means. If you have light going in, let's say that we won't go with that one yet. Where's mine? All right. So all we know is it does depend on the wavelength. So let's take a little triangle here. And we're going to shoot a wave at it. Let's actually make this a little bit steeper. But what happens to that light ray? So let's say this is 45 degrees. So because the indices of refraction are different, is it just going to continue through? And a light ray will just keep going that way? What's going to happen? Anybody? What is going to happen to this little ray of light when it goes through?
Can it reflect it?
Some of it might reflect, but some of it's going to refract.
Oh, refract. Just like half and half stuff.
So based on the law of refraction, what is the angle on the other side going to look like? If you like, you can outright solve it. But give me something about it.
What is the angle on the outright side, correct?
What's the angle coming out?
Well, I want to say it's the other side of that 45, and I'm probably wrong. Like 135, I guess that would be it. That's wrong.
No.
Too big?
What's the law of refraction? What's the law of refraction?
N1 sine theta equal N.
What is N1?
1.
What is in 2?
Two.
So y'all
So
senior,
what is
take it away.
theta 1?
Forty.
95.
What?
95.
45. So what does theta 2 equal? What?
130. No, it wouldn't be 135.
So it's plug that into a calculator and you get 20. 0.7 degrees. So what does that mean about the angle? What does the light ray do? Which way does it bend?
Down.
What?
Down.
All the way down.
Not all the way down, but it bends down.
It bends down.
So instead of, if it went straight through, the angle would be 45 degrees, but the angle is only 20 degrees. So it's less than half of that. So now when it hits the other side, what is going to happen? Let's say this is 30 degrees. What is the angle that this one has? How do we find that angle?
Don't you have to divide it by 2?
No, we're gonna do a little.
This side does.
We have to do a
What
little
side?
trig. So if that angle is 20 degrees, what is that angle? Okay.
50.
Let's take a step back. Ignore this blue line for a second. All we know so far is that the angle at the top is 30 degrees. These dashed lines are the normals of, so this is the normal for this, this is the normal for that. What is true about the angle between the normal and the side that it's coming out of or going into?
It's a 90-degree angle.
It's 90. So what is this angle on bottom? What is that bottom angle? All of the angles inside of a four-sided figure have to add to what?
360.
360. So 90 plus 90 is what?
180.
So that means that the other two sides have to add to 180. What do you have to add to 30 to get 180?
150.
150.
Mm-hmm. I
That
should have
boy
said
Cody.
49.8 just to be too little childish.
Okay. So this is a triangle. What do all the angles inside of a triangle have to give you?
180, right?
180. So 20 plus 150 is what?
170. 170.
170. So what is this angle?
10 degrees.
10. All right. So apply our little equation again. We got to figure out what is the angle of it coming out. So into sine theta 2 equals, we'll call it in 3, sine theta 3. What is the in value inside this thing?
2.
What is the angle going into the other, going into this side?
150, right?
It's 10.
Oh, yeah. 10.
What is the in value out there?
1.
1. And so theta 3 equals sine -1 of 2 sine 10 degrees. And that gives us
20.322. Right?
Probably close. I went ahead and did it's actually not 10 degrees, it's like 9.3 degrees, but it's close. So it's about 19 degrees. So yeah. All right, so this is just for this prism. But what if the n value depended on the wavelength? Well, if you had white light coming in, that means you have all of the different wavelengths. But if you had a purple light, it's going to refract differently than the other end of the spectrum, which is red light. So when you look at a prism, and I wanted to do one of these examples because we needed to do one. In general, light goes in, and at the end, red light will be like this, and this is a dramatization, so it's not exactly to scale. So which one gets refracted more?
The blue one, right?
I'm sorry?
The blue one? The blue
Yeah,
one?
the blue one gets refracted more. So does blue have a big or little wavelength?
A little.
A little wavelength, that's right. So this will be around 400. And red is around 700. So exactly right, the blue gets refracted more. This is what causes all sorts of different effects, but one of which is the prism. But the other is rainbows. And a rainbow is basically just caused by refraction through water droplets in the sky. So I won't get too far into the math because we're a little further back than I wanted to be. But this is called dispersion. So when light starts as one column of light that's all together and then gets dispersed into its different wavelengths, this is called dispersion. And it's all based on this fact that the index of refraction is a little bit different for white or I'm sorry, for different wavelengths of light. And in general, high frequency or small wavelengths get refracted more, and longer wavelengths get refracted less. So this dispersion large lambda and so this answers a question that a lot of people want to know, but don't necessarily understand. And you can, wow some people at your next parties, especially if somebody starts getting really deep. But people often ask, why is the sky blue? So well, using this information, why is the sky blue? Anybody have any hypotheses? So air doesn't have any colors, right? I'm sorry, go ahead.
So what, like the dispersion of the water molecules from the sunlight would cause the sky to be?
Yeah, I mean, it's exactly right. So you have the sun. And you have the earth. Let's actually do it like this. So the sun is giving off rays of light, and they come down and they hit Earth's atmosphere. And when the light hits, the red that doesn't get dispersed very much keeps going. It gets
So what does that mean? The color blue scatter more than the other colors?
That's right. The blues get scattered hard. So every point of contact, the blues get dispersed throughout the atmosphere. But the reds, more or less, just keep going. Okay? So the blues are like, and you can kind of think about it wavelength-wise, little tiny things like maybe, let's say, a 22 or a BB gun type thing. If that thing's going and you can think of it like a tiny thing. When it hits something, it's going to bounce off. It's going to ricochet. So the blues, the smaller wavelengths, ricochet a lot. And they keep ricocheting because they kind of get trapped in the atmosphere. Every new water molecule they hit, they kind of stay up. So all of the water molecules are kind of giving off these random blue scatterings from the atmosphere. But the red ones never got scattered, so they just come all the way through. So you get a lot of blue up top, and then the rest of the rays make it all the way down. This is also why the sun looks most white when it's straight up in the sky. What happens at sunrise or sunset? Well, then why are sunsets red? Well, it's the same idea, actually. When a white ray comes out and it hits, we'll say it hits here-ish. The red ones are the ones that make it through, and the blue ones get scattered around.
So what does that have to do with the clouds being white?
I'm sorry?
So what does that have to do with the clouds being white? Because the clouds.
So that's
play
a very
part in
good
this
question. Clouds actually scatter everything. Because they're so densely packed, everything ends up getting scattered. In air, there's only a few water molecules, so like very randomly throughout. So the blue ones get scattered very easily. So once they start to scatter, all of them scatter. But the red ones, I mean, they might only hit, 10 or 15 water molecules. Let's just throw out a figure. If they're going through the air, if they go through a cloud, they're all going to hit thousands of water molecules. So they're all going to get scattered just because there's so much to hit. So that's a great question, honestly. And I don't think I've been asked that one. But yeah, the clouds are generally white because they scatter everything. So they scatter all the light. But when the sun is going down, so the red doesn't generally get scattered, but for the same reason, the light has to make it all the way to you over here. The blue already got scattered out over here. And so the only thing that gets scattered over here is red. So sunsets look red because the blues are already gone and the reds are the only thing that's scattering in the air this far. But this is dispersion. It creates rainbows, creates sunsets, sunrises, blue skies. It's all based on this one basic fact of refraction. So, but great question.